Okay, we can start. And first, a couple of communications. And the first one is related to next week. Next week, Professor Ciolo will give the last lecture. It will be in Via Terracini, and next week I'm not teaching as planned in my calendar of the lectures. So we will see each other again in 2 weeks from now here, okay, here in Ravenna. And then I think it will be the last lecture in Ravenna. Then we stay in Bologna. And anyway, for next week, just keep in mind, so Professor Cialo will teach in Via Terracini, and she will tell you. And I am skipping the lecture because I am away next Wednesday. And yeah, so second communication. I'm not sure whether Professor Cialo already mentioned to you the dates for the exams. You are very few, so basically there is a lot of flexibility. The only thing is that we cannot register exams before June 7, 8, something like that. It is the second Monday of June where we can start. So it is around 8, 10. And but after that date, when we can register, it's no problem. Basically, we can take a lot of flexibility. And I'm not sure about. I have to talk to Serena about her way of delivering of taking the exam with her. And regarding my part, I am not sure about quiz or not quiz, because you are so few that probably an oral examination is better suited for your needs. Because given that the topic is also quite mathematical, probably if we have a conversation, it's better. But for the exams, we will let you know. We can also give you an indicative date, but where we when we can start. And let me just check. I think I'm not sure whether we can already make exams on June 7, maybe. And I'll tell you, okay, because I need to look at the calendar, academic calendar. But let me just check at our. It is very easy. Just one second. So let's. Let's see. So, okay, so I think we can go with June 7. Starting from June 7, we can get your suggestions for the exam. About you, when would you like to take it? As soon as possible, or yeah, okay. So I think we could fix a call for June 7, but let me check with the Professor Cella. Okay, and let's wait for her reply. Okay, that's fine. Now let's go back to our subject, and our subject is, as you remember, because we had a lecture just 1 week ago, we started talking about deterministic models, but we left something still to be discussed about non-stationary extreme value distributions. So I would like to go back to this part, which we didn't discuss. You may remember that I preferred to skip this part, the last part of the lecture, because the lecture was last week already quite heavy. So basically, I prefer to postpone it also because I wanted to check the codes. And so yeah, I think that the best way to introduce this final discussion on non-stationary extreme value distributions is to rerun the Po River experiment with the non-stationary GeV. So basically, let me get, okay, this is our theory. So you see that in the non-stationary GeV, there is the mean that is allowed to vary linearly with time, and also the standard deviation. In the standard deviation, we take the exponential because we want to avoid negative values in the value of the standard deviation. Of course, the standard, or better to say, it's not the standard deviation, it's the scale parameter, okay? So the scale parameter cannot be negative. So for this reason, we prefer, if we want to allow for change in time, to take the exponential. It is the exponential of a linear function anyway. And then remember that we concluded that we have 4 parameters to be estimated, plus the shape parameter. So the number of parameters is 3, which is the basis for the GeV, plus the additional parameter for the change with time of the location, and plus an additional parameter, so we get to 5, for the change in time of the scale of the distribution. I always make clear the number of parameters because remember that we discussed about parsimony, and we said that it is a desirable feature that we limit the number of parameters as much as we can. Of course, limiting the number of parameters reduces the flexibility. So at a certain point, we also would like to increase the number of parameters, but on the other hand, increasing the number of parameters implies the possibility of overfitting. Overfitting means that the model becomes very good in reproducing the data for which it is calibrated, but it becomes unreliable in extrapolation, and therefore overfitting is something that we want to avoid. So we have to look for a compromise. And we also introduced some criteria, the IC in particular, and AIC, or called as a whole IC, which is a way of measuring, when evaluating the performance of the model, both the number of parameters and the fitting of the calibration data. So, one final remark. Remember that it could be the change of location and scale. It could also depend on other external covariants, not just time, but for instance, temperature, which is changing along time. So basically, it's still a dependence on time, but through the dependence on temperature. This is particularly useful if you think of adapting the extreme value estimation to the predictions given by climate models. Climate models are particularly reliable in simulating the temperature. They are less reliable in simulating the extremes, for instance, of precipitation. And therefore, an idea could be that we explore, working with the past data, the dependence of GeV parameters, in this case, scale and location, on temperature. And then we estimate the parameters for the future by incorporating such a dependence on temperature, where the temperature is given by the climate models. This is actually something that is frequently done in technical applications. Okay, so now let's look for this Po River case. And in this case, we make a first estimation by allowing the mu to change, so the location. And then we make a second estimation by allowing mu to change plus the scale, sigma, to change. So the argument mul equal 1 means allow the location to change a long time, and the parameter, the argument sigl equal 1 allows the scale, sorry, to change in time. Remember that in order to inspect the variability along time of the historical data, you have to preserve the order of the data. So when we make the estimation, we don't sort the data in ascending order, for instance, to compute the frequency of not exceedance. We keep the original order. Remember that when you have a historical series, a time series anyway, that is ordered, it means that it is preserved, of course, the probability distribution. You can estimate the probability distribution. But if it is ordered, you can also estimate the change along time of something, of any statistics that you want. If you destroy the order because you shuffle the data or you order the data, you still preserve the probability distribution because same data, same probability distribution. But the features, the patterns along time are not preserved. So when we sort data, we cannot study after sorting the dependence on time if we don't keep the original order. So here there is in this code an additional complication, which is given by the need to preserve the original order of the data. So basically, when we compute somewhere here, we estimate the frequency. Let me see. And maybe it is called Frekner, frequency of not exceedance. It's here. So basically, this is actually this is the synthetic one. Sorry. Okay, let's go and estimated again. Okay. Let's move forward. Okay, I think it is this one. No, let's move forward. Okay. 1 second. Yeah, this is done in the previous example. In this code, we use to fit the GD, we use a package into R, so we don't need to preserve the data. It's already the package preserving them. Okay, so let me run this code and in a R console. So let's use this PC and okay. I'm not sure whether it's already there. Let's see. No, probably not. Let's give me 1 second. Project. Oh. And I prefer to use this PC because it's easier for managing several tasks. So this is not Windows. Okay, base. Okay, good. Oh, strange. Let me see. Let me get another mirror. Okay. Okay. This one was already there. Sorry. Okay. It's going. Polish. Let's see. Okay, it's going. Okay, good. Now, still. Okay. Okay, let's keep the console here. This is fine. Let me just change the font. So, okay, let's put 20. Okay, good. Here the screen, and then I can make a cut and paste from here. And let me just start by installing the package because I want to see if everything works. Okay, and it's fine. Let's see. Okay, and now the library. And if the library works, I think we can, okay, very good. Now we can estimate this one and until the diagnostic plot. Ah, yeah, okay, sorry, I forgot to download the data. So let me just go back here and let's do like this. Good teaching. Actions, perfect, and then explanation learning, good here, and then here. Okay, completed. This should go to C. Okay, to document here, and now it should go. Let's see if we can. Okay, good. Okay, perfect, and this is. Let me just. This is what I am plotting here is, let's get the code. It's the goodness of Pete for the yeah. Thank you. Okay, very good. Okay. No. This is your translation. Okay, perfect. And I think sorry. Was it the wrong page? Okay. So this is the diagnostic for the first fit. The first fit is allowing to change only the location parameter. And let us see here. This is fine. Okay. And we can also show the second one. So fit one. And this is the plot for location plus scale. There is not much difference, okay? We already discussed the difference between the two. It's a very tiny difference. Anyway, now what we can do is to plot, we already did this, the time varying location parameter. And the time varying location parameter, I think this is instructive to plot. So it's the time varying location parameter is of course a straight line because it's a linear change. We already mentioned that it's a very tiny change because the location, you see that it goes from 4,818 to 4,826. So it's really a very tiny change along 107 years. Which means that there is not, according to this model, a huge change in time. So there is not a huge change due to climate change, apparently. On the other hand, we see an increase, and this is consistent with what we expect. It's a small increase. So it's indeed small, but it's still an increase. Okay. And that's fine. So let's keep this in mind. And now we open another plotting window, brand new, okay, for the next plot. And let's go back with our code. And one thing, because we didn't discuss it last week, we discussed the archaic information criterion, and it is a very simple one. You see that there is a statistic that is computed depending on the likelihood, and the likelihood, the higher the likelihood and the better the fit. Okay, the likelihood, remember, is the probability to observe the data depending on the parameters of the GV. So clearly we maximize the likelihood because we want to maximize the probability of observing the observed data. This means that we are maximizing the fit of the distribution by maximizing the likelihood. So the archaic information criterion is computed depending on the likelihood. And the higher the likelihood, the lower the AIC. Remember that the lower the AIC, the better it is. But then there is a second addendum, the first in the right-hand side, which depends on the number of parameters. It is K, the number of parameters. So this means that the AIC increases for increasing number of parameters, so it increases the penalty, and the AIC decreases for increasing likelihood. So the better the fit, the lower the AIC, but on the other hand, the higher the number of parameters, the higher the AIC. In general, the coefficient 2 is allowed to change. This is what Akaike proposed, but there is another criterion which is called, let's forget about the corrected AIC, which we already discussed, okay? There is a variant of the AIC, which is called the BIC, the Bayesian Information Criterion, where indeed it is preserved the second addendum, but the first one is given by K, number of parameters, times the logarithm of the n, where n is the sample size. So it is a way to take into account the sample size of the distribution. These two parameters can be computed easily with R, but in R, one of the routine to compute the AIC and BAC compute the criteria for an object of class log likelihood, log leak. And so basically, what we get from the previous code, so GV fit and GV1 fit, so fit1 and the fit, it's not an object of class log likelihood. It's just a matter of convention of format. And therefore, we need to format the previous results, fit and fit1, to give to them the desired format. So the first instruction is that we have to create a class, log likelihood, for the object NLLH, which is actually the logarithm likelihood computed by the routine. So we first need to give the class, okay, and I had to work out how to make it because it was not so easy, but and then we have to define attributes to the same likelihood. So the number of parameters, which have to be named with the attribute degree of freedom, and then the number of observations. So if we do this, we are done with the first fit, okay? Just to give you an idea, fit dollar and LLH, this is the number. And now you see that it gives these attributes, class and attribute, okay? It is a way of labeling data into R. It's just a matter of convention. Unfortunately, these conventions change from package to package, and now we can compute AAC, fit, and LLH. And this is the AAC, and also we can compute the BIC. These two functions are included in the package ISMEV. Of course, these two numbers by themselves don't say anything. They do say something if they are compared with another model. So now we should compare them with the analogous results taken with the fit1 estimate. And the fit1, remember, is adding an additional parameter to the GV to regulate the change in time of the scale. So we have to repeat the definition of class and attributes, but this time for fit1. And of course, I have to tell R that the number of parameters for fit1 is 5. Okay, so here it is the second instruction. And now I can call AAC fit1 and BIC fit1. So you see that there is, according to AIC, there is a preference for the GV with non-stationary scale and location, the second one. You see that the AIC is lower, it's just slightly lower. In terms of the BIC, it is the same result from minus. Let's see, because it's negative. So yeah, the lower one is indeed for the first solution. So basically, these two criteria say that the stationary and non-stationary GV with only location changing is preferable. Of course, you could make the same exercise, and it is not particularly difficult, with a stationary GIV. And it's not here, but let's make it. The only thing that we have to do is to make another fit. And the other fit is, of course, we need to change here, fit 2, let's call it fit 2. And then we have to remove these two arguments. And then we get a stationary GV. And then we need to, you see that now we have only 3 parameters. And now what we need to do is to, again, give the attributes. So let me do this here. Plus fit2 log likelihood. And then let's, the attributes, degree of freedom is 3. Degree of freedom is the number of parameters, is another way of calling it. Okay? And then there is, again, this one, it's, I forgot, yeah, fit2. This one is fine. Attributes, fit1 is 5, actually. It's 5, yes. Because otherwise we cannot compare anymore. And then fit2, 3. Now it should be okay. Perfect. Now let's call AAC fit2. And it looks like it's the best one. It's preferable. And let's also call the BIC fit2. Let's see, I think, yeah, it's still preferable. So basically, at the end of the story, these statistics say it's better to use a stationary GV. And indeed, in view of the change of the parameter in time, I think it's indeed preferable. Everything is clear?
For any various models, BIC and AIC, when it is reduction, it's better.
Yes, yeah, the lower the better. Okay. Remember that when you are in doubt, in any case, doubt about a model, it is anyway a good idea to make the estimate of the design variable by using these 3 different solutions. And you will see that indeed there is a very minor change. Anyway, we have 3 estimates now, and we can also make this check. And this helps you also in understanding what is the technical implication, because remember that when we talk about statistical significance or statistical testing, like Kolmogorov-Smirnov, Anderson-Darling, or even AIC and BIC, some people rightly say that sometimes what is statistically not significant is very significant from a technical point of view. So basically, these people mean to say, when it's the life of people that matter, it's probably better to be more conservative, even if the statistics suggest a different solution. Just 1 second, I need to, okay, very good. Okay, so this is the results so far. Now, let's go back here, and we already have the plot of the time-varying location parameter, and we could get an analogous plot for the fit1, the second solution, but let's forget about it for now. And now let's look at the last solution, the nonlinear variation of GAV parameters. And indeed, there is a codified, theoretically developed solution for this. It is given by the use of what are called generalized additive models for location, scale, and shape. And the acronym is GAMS. And basically, these are models that are allowed to be to account for nonlinear changes. And we don't get into further details because there is a theory behind it, a theory that allows each parameter, so location, shape, and scale, to change as smooth functions of time, smooth nonlinear function of times. We need a package which is called GAMS, and also some additional ones which are needed in order to make the analysis that we want to do. So 3 packages in total. Let's install them. Okay, and it's also installing some dependencies. Okay, very good. And now we need to call the libraries. Oops, sorry. Okay. Okay, very good. There are warnings which are not. And then we need to prepare the data in order to be handled by this package. So we need to create a data frame which includes the annual max flow and the annual max year in order to account for variability along time. Let me clear the screen. And then note, annual max year must be a vector with the routine below, or let's see, annual max, yes, a vector. And therefore, we need to make this change, annual max year vector. It's while annual max year now, it would be a matrix. So let's make it a vector in this way, and then we can make our fit. And you see that again, there is sigma formula and nu formula, but let me see, sigma formula, yeah. Sigma. Okay, very good. Okay, so there is basically the location is allowed to change. You see that this is PB is representing the location, referring to the location. And the location is allowed to be a function of time, while sigma and shape are location and scale and shape are kept constant. So this corresponds to only the location be a function of, sorry, of time. Okay, perfect. This is done. And then we can also make another fit by allowing location and scale to change with time. Good. Okay, now let's look at the diagnostic. First, this one. And it's not a graph. And let me see, it's not a graph. Why? Let me see. I was expecting, I have to stay here. Okay, this one. Oh, okay, perfect. This is, let's forget about, okay, let's start from the top left. This is displaying the residuals of the quantiles versus the fitted value. So it's not a quantile plot. It is something that is called, worm plot. I will show you later more details about this. So instead of plotting on the vertical axis the quantile given by the distribution, it is, or better, it is, yes, instead of plotting the quantile of the data, because in this case it is plotting on the vertical axis, on the horizontal axis, the fitted values. So on the horizontal axis, we have the quantiles given by the distribution. On the vertical axis, instead of giving the quantile given by the data, it is displaying the difference between quantile given by the distribution minus quantile given by the data. And it is a different way of representing it, which may be useful for reasons that I will explain you later. Top right, same thing against the index. Actually, it is the same thing because plotting against, yeah, it's not really the same thing because here you can get the variability on time. Here you get the variability depending on the magnitude of the quantile. Here you get the variability on time. And then there is, sorry. Okay, the density estimate and the normal QQ plot. Let me see, because I think, okay, very good. And the normal QQ plot is basically giving, it's a quantile plot, but it is normalized. So you see that it doesn't give you the theoretical quantile in terms of the real values that have been observed, but it gives to you the quantile from a normal distribution of the frequency of not exceedance of observed and theoretical values. So basically, for each number, you get the frequency of not exceedance and or the probability given by the distribution. And then with the standard normal distribution, you compute the quantile. So it is called normal quantile plot. It's a kind of transformation of the quantile plot. I don't like it because I mean, from the point of view of an engineer, I prefer to see the confrontation between the observed data and the data that are simulated by the model rather than rescaling them. This is a kind of rescaling. Okay, but anyway, we can also get the same thing, and this is for fit.
What is the red lines?
Red lines here in the density estimates, I think these are probably, so these are the residuals. I think these are the, because this is a smoothed density, I think probably these are marking the points where I have the observations. And I think so, because they are like thick marks. And we should look at to make sure that the instruction of the package. Okay, so now let me go here. Of course, I can also plot fit1. I don't think we can see a big difference here. And but what is interesting to see is the change in time of the parameters to be compared with this one. Okay, because remember, in this case, we had a linear change, and now in the last fit that we made, we have a nonlinear change. So it's interesting how this change in time translates in terms of nonlinear change in time. Okay, and we can get it with the subsequent code. Before making it, before looking at it, let's look at the worm plot diagnostic. Okay. So let's look at the worm plot. Here is the worm plot. So it's still displaying. You see here we have the unit normal quantile and then the deviation. So basically we are still displaying the residuals of the models, so the errors, the estimation errors, against the observed values. But it is rescaled, so it's a normal quantile. It's not really a quantile deriving from the GV, and the same thing for the deviation. For the deviation, so the difference between the value given by the model and the values that have been observed. And why it's called a worm plot? Because in the ideal case, this plot would be a straight line, a straight horizontal line at ordinate 0, which means the residuals are equal to 0. And basically, they are not always equal to 0, of course. And so you see something going up and down like a worm. And what you see instead in dashed black lines are uncertainty intervals, or let's say it's the confidence intervals computed at the 95% confidence level, which means 5% significance level. What does they mean? They mean that if you get all the data within the two dashed curved black lines, it means that, the departures of the model from the reality are never statistically significant at the 5% significance level or 95% confidence level. Actually, you could accept at most here about 5 points, even outside these two dashed black lines, without compromising the statistical significance at the given confidence level of the model. Now, it's interesting, I didn't explore in this package how these confidence bands are estimated. I think there is some Gaussian assumption behind, and some also some homoscedasticity assumption. And let me better explain. This worm plot is also interesting because you could see that the departures from the model, from the reality, increase in some regions of values. So, for instance, if you have something like this, this is the worm plot where, let me just use the same more or less indication. So this is unit normal quantile. And here there is one thing that is not clear to me, which can be easily inspected. This unit, what does this mean, unit? Which, in my opinion, is canonical. So it means that you have a unit standard deviation of the normal distribution. And the other thing is this normal quantile is computed over the frequency of not exceedance of observed or simulated data. It doesn't make a big difference, but if one wants to be rigorous, this has to be specified. It doesn't make a big difference because the model is quite correct. And then we have the deviation here. And again, the deviation, it would be interesting to see if it is computed in terms of normal quantile. I think so, but it is not explicitly written here. So you have here 0, and then you have this horizontal line. So ideally, the model is the test displays a horizontal line at 0, but you have some departures, and this is why it's called the warm plot. It may happen that these departures increase, for instance, for the higher values, which means that the model is not reliable, it's less reliable here than here. And this is a useful indication of the spot, which you can get also from the quantile plot, but not as here as here. So this kind of diagnostic is suggested in particular from the technical departure from homogeneity of the homogeneity means constant variance, constant variability. In this case, you have variability that is not constant, which means heteroscedasticity. And it is called in English both scedasticity or shedasticity. It depends on the English and the American English. And then another interesting thing is, okay, we have these bands, how they are computed. I think they are computed under the assumption that it is data Gaussian, and therefore you can easily compute basing on the residuals what is the level of uncertainty under the assumption of Gaussian distribution. But this is something that should be inspected. Okay, this is the warm plot. So we learned another diagnostic which is interesting. Now, let's compute the AIC and BIC, and these don't need any transformation. When you fit with this routine, the result of the fitting is already an object of class log-link. Okay, so sorry, let's go back here and here. Okay, so fit and fit one. In terms of AIC, the lower is fit. So again, it says that the lower the number of parameters, the better it is. And in terms of the BIC, same thing. Okay, and then it's interesting to compare with okay, here we are. So let's compare with fit. No, it's not comparable. It's not comparable because of different.
Why was the previous one?
Because I think that probably it's computed in a different way. Let me see. BIC. So let's look at. Let's try to understand. I'm not sure why, but names fit NS. Let's see. Okay, family parameters code control. Let's see what is the likelihood here. Family parameters code Y control weight goodness. Moving so let's check. So fitness. And there is nothing. Okay. So let's see parameters code Y control with type method context converge of the residuals. Number of observation, more opinion, more coefficients, more terms. See, coefficients, more link, more. Let's see, fitness AIC. See what is okay. This is the same as before, but I think that probably it is simply inverted the sign, which means but okay, let's see parameters. mu sigma nu. Okay. So call control. No. Okay. I think one possibility is that it gives a positive value for it, so it's just a change of sign, an inversion of sign, and then AIC probably gets precisely value of given by the routine. I'm not really sure. This is something interesting to be inspected. Okay, and one more thing could be, let's look at. Okay, sorry. Let me check what is it is okay, GAM is GAM LSS. See? Okay, let's look at this. Arguments, okay, this is fine. Details, let me see, AIC. AIC, the archaic information criterion, let's see, likely. Weights, a better weights. Okay, no problem. Detailed, maximum penalized, just maximum penalized. Weights, and probably SBC, let's see. Okay, it's still positive, and for some reason it is giving it in positive, which maybe simply there is an inversion of sign, which means that if there is an inversion of sign, it is a bit strange anyway.
For example, if we have two models, the AIC for one model is positive, for the other one is negative. How would you compare it?
Yeah, of course, we have to understand here how it is computed. It looks like still if the lower the better, but I don't understand why there is this change of sign. So could it be log likelihood? Let me just think, because if it is decay, no, it cannot be log likelihood. It is something that is here which doesn't work. I think the routine BIC simply gets the argument from the fit1 NS, because if I make fit1 NS, it gives the same number, precisely the same number. So it means that it goes straight to getting the component of the list, the value given by the list, which is a bit strange because it is a component. Maybe it's a component from the same package. I think so, because this one, let me just check. Touch. Just check. Yeah. Anyway, I think there is the possibility that here, when I uploaded, I put these libraries, maybe that they uploaded a different version of BIC and AIC with respect to what is uploaded by the package ISMEV. Because ISMEV, I think, incorporates AIC and BIC, and in the same thing, in the same way, maybe that GAMS incorporates a routine for computing BAC, AIC. What we could do is to try to. Actually, it is a bit strange because I see
it's related to computation in the various packages.
Yeah, maybe. Yeah, for sure. But this is a possibility. But still, it is still working here with the same. So it is really, it's really strange. And maybe that it was also a problem with, because they are comparable. Maybe the problem was also with the classification of log likelihood that I gave here. So I think that what you should work on is this class and the attributes. So I think that given that fit NLLH is fit, oops, let me see. Okay, so this is positive, which is okay. But then if it was negative, I think maybe there is something here that doesn't work. It is this problem in the definition of the class. And I still think that it should work and it becomes negative, but maybe that the object of class logleak, which is to be inspected with a search, so R project object plus logleak. And here, basically, one should look whether logleak extract log likelihood. So, the sign has to be, it has to be verified, the sign that you get. Maybe that what they do is to provide always a BIC that is positive, but still it's the lower the better, okay? And so if you, basically this means that in order to get it positive and the lower the better, you should get the likelihood maximized, or yeah, it is to be studied the sign, okay? And maybe that if you change the sign, the higher the better. If the higher was the better, then it means that in this case, the BIC and the AIC are better for the nonlinear change of model parameters. Maybe, but it is to be verified. Anyway, what it is important to see, first of all, is okay, to see the time varying return level. And let's see, this time varying return level means that against time, I can put a change in the return period. Let's look at the plot first. And this, what you get from here is a time varying 50-year flood estimate, depending on time. And what you see, first of all, the magnitude of change is within more or less 10% of change, which is not so negligible. I think with respect to the first estimate, linear variation, it's a change that is a bit more pronounced, even if it's not very large anyway. 10% is not a very large change. But what we can see from here is what happens in linear reality. If you allow nonlinear change in time, you may get something that is not corresponding to our expectation. Because you see that there is an increase up to 1980 and then a decrease. A decrease that goes back more or less to the original story, to the original state. And therefore, if you fit a straight line here, you would get an increase of about 200 cubic meters per second, which is comparable, in my opinion, to the increase that we noticed with the linear variation in time. And first of all, I mean, this means that by allowing a nonlinear variation, you may get something that is not very meaningful because it doesn't correspond to our expectation that we should get a max around 1980 and then a decrease. And if I want to extrapolate this in the future, what should I do? I mean, it is a magnitude of change that is larger than the linear one, but probably is affected by more uncertainty. And because, I mean, if I have to extrapolate, I don't know how to extrapolate this. And so it's much better to extrapolate the linear change because it was giving a less significant change in long time and something consistent with our expectation that the peak flow should increase in the future. In this case, I mean, this is impossible to extrapolate. And this, I think, is the most interesting part of it. So even if we conclude that the BIC and the AIC are better, and even if we conclude that through the quanti-quanti plot or the probability plot that the estimate that we got is better, on the other hand, we see from here that this is a model that probably is over-parameterized, is overfitted, because, I mean, this is impossible to use to make a prediction. So this is the important result. So it is for sure important if you inspect what is the inconsistency in the computation of the AIC. And by anyway, keeping in mind that it's not wrong what we did in the previous case. It's just a matter of different representation by different packages. But I mean, please inspect it so we clarify this doubt. But what is really significant, I think, is this change of the 50-year return level flood estimate a long time, which corresponds to a similar change, because remember that this is the fit that we get from the solution where only the location is allowed to change in time. So it means that even the location parameter has a similar change, and which is something that is not really reasonable. Now, what we could do is to adapt this code. So let me see, sigma, okay, fit. We could use here fit1 and see what we get. Okay, so let me compute. Let me change this. Okay, so fit1. Okay, fit1. I think we can keep this. Okay. 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 Oh. I think this is fine. Okay, this is fine. Plot. Let's see. Yeah, it's similar. It's not precisely the same because you see that the difference between start and end is different, but more or less the result is similar. So again, impossible to extrapolate. Okay, good. Well, I think that here it's okay. I apologize for the step-by-step and trial and error pathway that I followed, but I think on the other hand that it deserves some consideration, and I hope that you can take the opportunity for learning more from this consideration and trial and error procedure. Okay, very good. Now let's go back here, and I think, oh yeah, we can compare also different retro periods. So let's see, I think that we can make this plot directly. Yeah, because, let me see, this mistake here. Let me just recompute because I'm not really sure what I did. So let's do this. Okay, good. And now let's try again. So this one worked. Okay, good. Let's see this. It should work. No, plot here. Let's see. Let's see where is the problem here. L15 type, L9 with the epsilon range. Okay, this is fine here. At 11, okay, here there was. Okay, good. And now this one, lines. There was a paragraph missing here. Now this one. Good. And let's see now what is that? Okay, this is time varying retro levels. This is an example of a more refined. Oops, sorry. Let's see, grid. This way is even more refined. Okay, and you see the change for different retro levels. This is also interesting to see what is the magnitude of change in general, given by a distribution. The magnitude of change on the peak flow estimation. On this is a consideration that is valid for any extreme value that you estimate. The magnitude of the change from the 20-year retro period to the 100-year retro period. And you see that here the change is from 9,000 more or less to 10,000 and a half, more or less. And it's about a little bit more, 15%, let's say. So from the 20-year retro period to the 100-year retro period for this distribution, the change is 10–15%. Of course, it depends on the distribution parameters. And so for different parameters, you could get higher changes. But the essence of the message is, if you consider that the level of uncertainty when you measure extreme flows is around 20–25%, you understand that when we talk about different retro periods, very often we navigate within the limit of our uncertainty. By the way, you had an interview with Professor Di Baldassare. I forgot to say this earlier than that, but in general, try to have a look also for the future at the contribution by Professor Di Baldassare. Probably you already had a look at them, but when you prepare for an interview, it's a very good thing to look at the member of the committee and have a look at their contributions. Yeah, you did it probably. Yeah, very good. Because yeah, because when we worked together, we worked actually on the uncertainty of river flow estimates, peak extremes.
So the first article is here you published with Professor Tiana. So
Yeah.
about this,
Yeah, you read it. Okay, this is very good. Okay, very good. Okay, so now we have finished here. And if you get, I will take care of correcting this missing paragraph. And if you inspect the issue of AC and BAC, I will do the same, and then we can consult together and clarify this discrepancy. But just remember that it's a doubt that is related to the simple fact of making statistics about the goodness of the fit of a model. Is not very relevant. What is relevant is the technical implication that we discussed. But let's, anyway, even if it's not relevant, it's a doubt that we have to clarify. Okay, good. Now, I think that definitely we can consider this part of extreme value distribution concluded, extreme value estimation. And remember that this is something that is not frequently taught in the university courses, especially the non-stationary part of it, with the return period changing in time, which means that it's the extreme flow estimation that is changing in time. And this is something that is not very common because it's relatively recent. And therefore you can consider it like not a distinguishing feature, but a characterizing feature of your CV and your experience at Unibom. Okay, very good. Now, let's go to the deterministic models then, and let's restart our discussion on this topic. So basically, we already started discussing that, but let me give you a more refined introduction by first depicting a scheme of what a deterministic model is. And remember the definition, which you can find on my website. And the definition is that deterministic model for any given input always produces the same output. And this is not the same for a stochastic model, that for a given input, anytime that you run it produces a different output. And just remember this definition because it is essential. So deterministic means one input, one output. Deterministic, one input, one output, one output. Always the same, stochastic. Stochastic means many inputs, many outputs. Just keep in mind this distinction because it guides you in understanding the difference between the two approaches. Anytime that you see that a model is random implies this distinguishing feature. So if you use one input, you get many outputs. In general, you can use many inputs and you get many outputs. But even if you use only one input, because you can, for instance, assume that in your stochastic model, you have the input that is certain, but still, if you preserve the fact that this unique input gives many outputs, then it's stochastic. So in the model components, input data, model structure, and model parameters, it's just sufficient that you introduce one element of randomness. For instance, maybe parameters that are random, and then the model is classified as a stochastic one, meaning random. So if you include one element of randomness, which is embedded into the model, then even if you use a certain input, if you have a randomness in the model structures, then it becomes a stochastic model. And remember that stochastic can be considered a kind of a synonym, not really a synonym of random. What is the difference? The difference between a random variable and a stochastic process is that the stochastic process is a family of random variables. We already defined this, which means that you describe a sequence in time or a sequence in space where each value at each time is a random variable, but you put them together because the order matters, okay? And maybe the order in space, and you obtain something that is called stochastic, no more random, because random refers to a single variable. Stochastic means that you have a sequence of random variables, or better to say, recursively speaking, a family of random variables. So basically, a model is something like is something like where you get into the model with an input, and then you take from the model an output. Okay, this is a scheme that can describe both a stochastic and a deterministic model. And here, usually you have parameters. Usually you have parameters. I say usually because a model can, in principle, be non-parametric. So it can be something that transforms the input into the output with no parameters. Usually the model, in order to give it flexibility, has parameters. And these parameters are part of the model structure. So again, this scheme can describe both deterministic and stochastic model. But in the deterministic model, by definition, you have one input which generates always the same output. If in this scheme you introduce something that is random, maybe the random input, maybe the random parameters, maybe a random model, then you get random, a stochastic model which produces for any rank a different output. Okay, and it just suffices one component. So it can be a model that is deterministic where I use a random input. And then, of course, every time I run it, I get a different output. It can be a model that is deterministic, but with random parameters. And therefore, every time that I run it, I get a different output. Perfect. Now, why deterministic models? We discussed the pros and cons. So first of all, remember that the fact that a stochastic model generates many outputs, it's an asset because it gives you a distribution of it, a distribution of outputs. And therefore, you can get also an estimate of uncertainty if the model is well done, is representing the process, the reality in a good way, you get an estimate of uncertainty. On the other hand, in order to get this range of outputs, you need many simulations. And therefore, the stochastic model in general requires many simulations. Many simulations because usually these models are complicated and you cannot get the distribution of the output analytically. In principle, this is possible. There are examples where you can get, for instance, let's suppose that you have the output X, which is given by simply Y. Okay, this is the model. It's deterministic. It's deterministic and it's non-parametric, by the way, because it says that the output is equal to the input. And it can be, for instance, when you want to estimate the volume of water a long time that is delivered by a rainfall over a roof, the model is non-parametric. You just measure the rainfall and then you convert the rainfall into, multiply the rainfall for the area of the roof, which is not a parameter, it's an input data, and then you get the volume. It's like something like this, where here you will have a constant C. Okay, because the constant C is the area of the roof. Anyway, if you have a model like this is non-parametric and it's deterministic. If you want to transform it into a stochastic model, you can write that Fx, which is probability distribution of x, is equal to C for the probability distribution of x again. And this
or y?
No, because it's or let's say, okay, let's put y. Let's put y, but in this case, fx, yeah, okay, this is correct. And therefore, one could say, I think you can also write probability distribution of x, but let's keep this in this way because it's fine. And so basically, this means that the probability distribution can be computed analytically. Okay, and of course, you may say, I don't know the probability distribution of y, but the probability distribution of y is related to the probability of distribution of x, meaning that the probability of not exceedance of a given value of x is equal to the probability of not exceedance of a given value of y. So I think here you can substitute it. But in any case, what is important as a concept is that when the model is very simple, you can easily translate, given the probability distribution of the input, you can easily compute the probability distribution of the output without making several simulations. But when the model is complicated, complex, non-linear, and whatever, then you need to go with simulation. And this is the first disadvantage of the stochastic model, and it's the first distinguishing feature of the deterministic model. So why climate models are deterministic, why people are not trying to consider all the sources of uncertainty? Because with climate models, we are limited in the computational resources. We cannot afford to generate several runs of climate models. And this is, of course, something that is a good thing for deterministic models. So when we discuss here the pros and cons, the added value is one of the added values of deterministic models is the computational simplicity. And then another added value is transparency, as we discussed, because very often the deterministic model is more easily understandable with respect to something that works in terms of probability distributions. And for instance, here you see that transforming from deterministic to the stochastic form, we have to make a reasoning on how to make this transformation. And it's not easy, even if the model is very simple. On the other hand, they have limitations. So a first limitation is that the deterministic model, given that it doesn't account for uncertainty, needs to be based on a realistic and reliable representation of the system. So if you allow for uncertainty, you can, in a way, say that what you don't know is accounted for in your uncertainty estimate. And provided that you are able to estimate uncertainty in a reliable way, you don't have any more to bother about how to quantify the human impact. This is the usual question. Like, okay, you are modeling a catchment or you are modeling air pollution, and how to quantify the human impact in terms, for instance, of of the human influence on the direction of on the wind direction, on the ocean currents, on how to estimate it. This is a classical question. And then if provided that I have a good method for estimating uncertainty, I can say, I don't care about estimating any tiny detail. It's just enough for me to estimate, to get a best estimate according to my knowledge, plus a good uncertainty estimate, and I can make engineering design. And this is something that allows you, in a way, to make simplifications because you account for uncertainty. If you don't account for uncertainty, you have to be very precise in structuring your model because uncertainty is not known. So the only way to get out from this problem is to say uncertainty is negligible. And if you cannot say uncertainty is negligible, then it's a big problem because you end up with an estimate which is known to be uncertain, but you cannot quantify uncertainty. So it's much better to get an estimate that is maybe less precise, but with a good uncertainty estimate. And this is a first limitation. Second problem, and how to make calibration. Again, we are not accounting for uncertainty. We cannot account for uncertainty. And therefore, these models often are quite complicated because they attempt to describe any tiny details of the physics, of the nature. And then they include many parameters. How to estimate these parameters? It's already a problem how to estimate the parameters of a GD, and we are computing AEC, BIC because we want to make sure that the number of parameters is well proportionate with respect to the model complexity. In this case, the model is extremely complex, and you don't have any way of really understanding whether they are over-parameterized or not, unless you make some complicated testing. So this is a second problem with the application of deterministic models. And then, of course, there is the problem that the random variability, the stochastic variability is not captured here. And but in a way, if one had to say, what kind of model should I select? I would just say, depending on the scope of your application, on your target. So, because both of them present distinguishing features. And therefore, we are not here to say, forget about deterministic models. Because in some situations, they have indeed distinguishing features that we need to learn how to understand. Okay, so let's make a break and let's meet at 10 to 4, and then we stop at 4:25 as usual. Thanks a lot. Okay, Rada is connected. Okay. One more thing. As an introduction to the second part of the lecture, deterministic models. We already discussed last week that there are several examples in the literature where deterministic models are used and uncertainty is then estimated for their predictions. In this way, we are resolving or trying to resolve a limitation, the last limitation that we mentioned of deterministic models, the lack of an uncertainty assessment. And we try to resolve this limitation with a kind of post-processing. Sometimes also these techniques are called biased correction. And so deterministic models are used like for predicting climate. And then the bias is corrected to compensate for uncertainty. So there is implicit in bias correction an estimate of uncertainty in terms of bias. So in terms of distortion of the location of the average of the prediction. And then after assessing the uncertainty in terms of bias, the bias is corrected. So this is an attempt to resolve the limitation of lack of uncertainty assessment. Of course, for bias correction, we are not really correcting uncertainty. We are only correcting the bias in the average. But sometimes there are other bias correction techniques that are not limiting themselves to the correction of the average, but they correct the average and also the quantiles of distribution, which means that they correct not only the average, but they correct also the extremes, for instance. And this, an example is what is called quantile delta mapping. So it means quantile correction. When you apply these techniques or you deal with estimates that have been obtained by applying these techniques, and in general, for any stochastic representation, it's important to check the assumptions. So to check how uncertainty was estimated. Because, uncertainty assessment is a simple word to say, but then the problem is it reliable? And therefore, in order to assess the reliability of uncertainty assessment, you have to check the assumptions. To give you a very trivial example, if you correct the bias only in the mean, you are assuming, and if you say, I corrected uncertainty, I corrected for uncertainty, but you only corrected the bias in the mean value, you assume that uncertainty is just given by the bias in the mean value. If there is a bias in variability, if there is, you are not accounting for it. So it is extremely important when you deal with uncertainty assessment that you check the assumptions and remember that for environmental models, providing a reliable estimate of uncertainty is really challenging. It's something that, from a research point of view, has several implications that are still unresolved. So try not to be just satisfied by uncertainty assessment. Try to understand how it was obtained. In general, when you get predictions, you have to carefully check models, assumptions, and therefore models means also uncertainty, etc. One potential problem of deterministic models is that it looks like we are separating the challenge of getting a prediction from the challenge of getting uncertainty. So we are in a kind of considering uncertainty as a separate problem with respect to getting the prediction. Actually, it's not a separate problem. They should be included in the same problem. So getting a prediction should go along with providing an uncertainty assessment. this helps a lot and simplifies the problem in many cases, rather than trying to seek the best model and then concerning about uncertainty. Okay, so let me give you a couple of examples of deterministic model. Climate models, we already discussed them, so let's forget about this discussion. Just I want to remind you what I think is a quick overview of how we get predictions from climate models, because we get predictions from deterministic models, but we are also aware of the inherent uncertainties, and therefore we try, in most of the cases, we try to resolve uncertainty by running simulations from a limited number of models. And therefore we obtain a quite over range that we assume to correspond to uncertainty. Actually, very often this range is just a subset of uncertainty, because in order to account for the full set of uncertainty, we should run many different models, not just a few of them. Usually, we can perform only a few runs, and therefore the resulting uncertainty estimate is very often not comprehensive. This is a quick way of saying it, and a quick way of reminding you that you have always to wonder about uncertainty, how it is estimated. So if you look at IPCC, try to really look at the details on how they estimate uncertainty. And then let me go with another meaningful example, the so-called bucket model, which is a widely applied model in environmental sciences. And this is a very simple scheme of a bucket model. So, and this refers to the application of a bucket model to the computation of runoff after a precipitation. Look, runoff is what is resulting from precipitation minus evaporation minus infiltration. So it is the local contribution to river flow formation. And then the runoff is collected by the river. The runoff from the hill slopes is collected by the rivers, and you get the river flow. And I think a very meaningful example is the roof of an house. You have precipitation, and if you exclude infiltration, you shouldn't have any infiltration, because the roof, unless it is a green roof, shouldn't have any infiltration. And if you exclude evaporation, because you take this assumption, precipitation is totally converted into runoff. And then the runoff is collected by the pipe, the vertical pipe that goes to the sewer, which is the river. So the vertical pipe collects the runoff from the roof and forms then the river flow inside the pipe. And if you have a green roof, you have to consider also infiltration, which is in a way mitigating the runoff formation. And the bucket model is very often used in this context, but it's also used in many other contexts, because it's a simplified input storage output model, where the bucket accounts for the storage. So you can also apply it to the carbon cycle, where you have carbon production, for instance, from burning fossil fuels, and you have a carbon storage and the carbon sink, for instance, in the oceans, and then you have a release of carbon to the atmosphere, which is the output from the bucket model. So you can consider you can use the bucket model for many applications. This scheme, as I said, it refers to runoff. So you see that the input is precipitation, and then you have an output given by evapotranspiration. And then you have a soil capacity, which is the vertical pipe of the bucket, which you can divide in a saturated zone and unsaturated zone. And you can compute, according to some laws, the base flow from the saturated zone, for instance, like a bottom discharge. And then you have the interflow, which is the flow from the unsaturated zone, which is computed according to another law. And then you have the overland flow when the bucket is full. Everything that rains over a saturated soil, it's transformed into overland flow. And then these three components form the total runoff. And this is indeed a very meaningful example, and it is even more meaningful example of the linear reservoir, which I think, did we discuss it already in the first semester? Yes. The linear, yeah, okay, perfect. And I think we integrated it, correct?
Yes.
Yes, perfect. So let me just then summarize how it works very briefly. It is a simple bucket model, which is simplified in order to make it linear, because the scheme that you see over the screen is characterized by, you see, a base flow that is computed according to a given relationship. The interflow is given by other relationship, depending on the storage, and an overland flow. The overland flow is governed by a threshold, which means that when the bucket is full, as I said, everything that rains over the full bucket is transformed into overland flow. But this is activated only when the bucket is full, and therefore is governed by a threshold. The threshold is typically low here. So if we want to simplify this model in a way that the total runoff is computed as a linear function of precipitation, we have to introduce proper assumptions. And an assumption may be to simplify it through, first of all, only one release from the bucket, because in this way, the release is not governed by thresholds. There is only one release that is always active. So you have this bucket model where you have a bottom discharge, and you have here the runoff, let's call it Q, and here you have the precipitation, and here you have a storage W, and the W depends on T, Q depends on T, and precipitation depends on T. And actually, the relationship between, first of all, here you have an unknown, which is Q, a known input, which is T. Let's forget about evaporation and transpiration. And then you have a state variable W, which is still unknown. So basically, as we discussed, what you need is two equations. And one first equation is simply mass balance. So Pt minus Qt is equal to the WT in the V. This is mass balance. And remember that we said that anytime that we want to account for storage, we need to introduce a differential equation. So unfortunately here, if we neglect storage, it would become very simply Pt equal Qt, like the roof, because the roof doesn't make it, or let's say makes a usable storage. And but if we want to account for storage, we have to introduce a differential equation, and which is in this case a total differential equation, because the dependency is only on time. There is no dependence on space. And then we need a further relationship. And the obvious way of identifying the further relationship is to connect WT with Qt. So to find a relationship connecting them. Actually, what we know from our knowledge of physics is that the outflow from a bottom discharge from a bucket is related to the water content squared. And it's actually the opposite is let me see, W is equal to the square root of the water content. So because it's the square of the velocity that is connected to the water content, so the flow is connected to the square root of the water content. It's all linear. But if we want to simplify it, we can simply make it linear and say that Qt is equal to Wt divided by a constant K. This is constant. In this way, we already discussed that. We already discussed that by combining these two equations, we obtain a linear relationship. So basically, we can write that Qt is a function. The result is after integration is a function of Pt, where this function is linear. This is the linear reservoir. Okay, and we don't need to get into the details of the integration because I think we already discussed it. This bucket model is a very meaningful example. And then, as I said, it's deterministic. So there is no provision for uncertainty. If you want to account for uncertainty, what we can do in this very simple model is, for instance, assume that k, the parameter k, is a random variable. And then it means that anytime that I run the model, I pick up a value of k from the underlying probability distribution, and I get a different output. And of course, in doing that, then I have to make sure that still mass balance is preserved, but this is not really a good problem. And on the other hand, it's clear that it becomes quite the model remains linear, but it becomes quite complication. Okay, now let's try to get better into these deterministic models, how they are structured. Classification, as usual, helps in understanding how these models are structured. And first, let's distinguish the deterministic models into two main categories. And the categories are the one of the process-based models, which is the counterpart of empirical models or black box models or gray models. What's the difference? Process-based models, which can be also called physically based, because very often the theory underlying our models is the theory of physics. But actually, I prefer not to say just physically based, because in this interdisciplinary world, growing interdisciplinarity, sometimes when we say physically based, some people say, and what about chemistry? What about biology? What about other laws that are based on different sciences? So a more comprehensive term is process-based model, where with process-based, we mean models based on the application of theoretically based laws. And theoretically based on what? On our knowledge. So it can be, the underlying laws can be the laws of physics, can be a mix of laws of physics, laws of chemistry, laws of biology. And the important thing is to emphasize that under this category, there are models whose equations are based on our knowledge and therefore theory of the underlying processes. Sometimes we don't know these processes, or we don't know with full details. And sometimes we know them, but they are too complicated, these laws, in order to support the application of models. And therefore, we try to simplify them, like in the linear reservoir, by introducing an empirical. So here you see this is really physically based, it's mass balance. This one, yeah, you can interpret it as a conservation of energy, but actually it's an empirical law. So this is already a model that we cannot call fully process-based. I prefer to call it empirical, or in some disciplines, they call it conceptual. It means that the concept is emulated, but not really the underlying rigorous laws. And you can also call it a gray box model. I wouldn't call it a black box or a fully empirical, because a fully empirical model is a probability distribution where no constraints are imposed on the structure of the distribution. No physical knowledge is used to condition the structure of the distribution. Then it's fully empirical. And it would be fully empirical if I completely ignored also the mass balance, and I just try to reconstruct through something that ignores the physics, the outflow from precipitation. Okay, so now you know what an empirical model means, and you know what a process-based model means, and you know that there is a gray zone, which is something that is in between. And recently, there has been a lot of work on theories to transform deterministic models into stochastic models in a way that is not just a post-processing of uncertainty, but in a way that tries to account for uncertainty already in the model structure, and the output is given directly in the form of a probability distribution. Just to let you know that even if we try to make this classification, deterministic versus stochastic, process-based versus empirical, keep in mind that there is a gray zone. And the gray zone very often is the most interesting part of it, because it offers a good compromise between reliability and complexity. Reliability in the fit, and complexity in reliability in the fit and capability to make extrapolations. Very often this gray zone is what matters. Now, let me introduce what I think is an interesting option, at least because it is increasingly popular: machine learning. Machine learning is part of artificial intelligence. Indeed, many of the artificial intelligence tools are based on the application of machine learning. Machine learning goes back, at least in the current science, meaning it goes back, meaning the science that is applied in several disciplines by several researchers as routinary methods, at least 25 years. So it was the early 2000s when we learned about neural network. It was the first type of machine learning models that were proposed. And then they were modified in several other types. Interestingly enough, these models were born as deterministic models recently, not really very recently, but in particular recently. They were born as data-driven approaches and deterministic models. Recently, there has been an expansion of interest in machine learning methods that are physically constrained, which means that you introduce some physical conditioning in it, based on mass balance, based on energy balance, and formulations of machine learning models into a stochastic framework. We will see how this can be done. Still, it's an open question how to estimate uncertainty for these methods. Methods that, since the beginning, they were clear in their distinguishing features and limitations. I said that in the wide science, they were applied starting widely about 25 years ago, but actually the first applications of machine learning go back in the far past. Since we had the availability of the first computers, we learned that these computers had the capability of developing some kind of artificial intelligence, looking at a relationship between input and output, and then decipher this relationship between input and output in an automatic way, without bothering too much about the physics, but only bothering about the reliability of this interpretation. What made a big difference during time in the past 25 years was the computational efficiency of these models, was our availability of computational resources, which allowed to apply these methods widely. In order to be clear, what determined the explosion of artificial intelligence was not the invention, creation of new methods. It was the availability of the supercomputers, the super data centers, which allowed these machine learning approaches to be applied also at the very large scale of exploring the whole web. So it is artificial intelligence is not something new. It is something that was already known 30 years ago. Yeah, just developed because 30 years ago we didn't, but even 5 years ago, we didn't have the opportunity to browse the web, to manage so huge data set with these methods. And what motivated this explosion was the real need of find a way of managing the increasing information that was made available, especially in Earth observation by satellite data, by several informations that now we have available, but we didn't have the means to really look at it. So what is machine learning then? And it is a computational method that allows computers to learn about patterns and relationship without being explicitly programmed for it. So without any additional information that goes beyond input and output relationship. Of course, in order to make it reliable, you need a lot of data. So in the past, we didn't have this explosion, also because we didn't have enough data. In fact, the first applications of machine learning were in the management of the internet traffic, because in this field, they had already 30 years ago a lot of data. But in the management of natural resources, we didn't have the means of using it. And therefore, this is what really made the difference, information and computer center. But the methods are not really new. And the methods that are applied now in artificial intelligence are still based on neural networks and some variants. What has changed during time is the need and then the willingness of researchers to try to constrain these models based on physical consideration. Because for our purposes, which is environmental analysis, these methods were criticized because sometimes they were physically not meaningful, like mass balance was not preserved. It's not necessarily preserved, because by looking at the input-output relationship in the presence of uncertainty, mass balance is for sure not preserved. And this triggered a very interesting discussion. Like some people said, those that are more linked to a physically based approach, they said, this is just crunching numbers, and you are not respecting the laws of physics, and therefore it's not reliable. On the other hand, the counterpart said, but these are really outperforming physically based models when a lot of information is available. And then the other group said, yes, but you don't have enough information, and therefore you are just ending up with overfitting. Indeed, overfitting was and still is a problem. So these methods, they include a lot of parameters. And a lot of parameters because in order to learn from the data, they need a lot of flexibility. They have to try any possible relationship. And therefore, they need a lot of flexibility, which means a lot of parameters. So it's still a problem, the fact that sometimes they are very good in fitting the data, but then when you make extrapolations, they fail. So the discussion was really interesting. At the end of the story, of course, a compromise was found. Like, okay, perfect. Do we want to impose conservation of mass? This is for sure possible. On the other hand, keep in mind that, and this is what I am always objecting to my colleagues, in the presence of uncertainty, conservation of mass can lead to bias. So, I mean, because if you impose the conservation of something that cannot be imposed because the input is uncertain, so basically you constrain the output to an uncertain input, and without allowing for uncertainty, then you introduce a bias. So let's suppose that your measurement of rainfall is underestimated, so you have a 10% less. Then, of course, you have a bias in the measurement. If you impose conservation of mass, you get the same bias or more or less a corresponding bias in the estimation of river flow. So, I mean, the discussion was very interesting and still is very interesting. And it's something that indeed is also stimulating, because it's clear that this is a new opportunity. Artificial intelligence is a new opportunity. On the other hand, it's something that needs to be tuned in a proper way in order to be used. And next time, I will tell you a meaningful example, which is random forest. Why it's meaningful? Because random forest is including randomness, random forest. And this is something that is widely used today, is not the most used in environmental assessment, and we will discuss why. Okay, I think we can stop here for today, and I will make the changes that I spotted out in the previous lecture, and let's get in touch, keep in touch for the AAC, BAC. It's an interesting question that we left open. So thank you very much.
Thank you, Professor.
Thank you, Rada. Next week, I'm not teaching. At the start of the lecture, I said that. And I'm not teaching, I already anticipated it, but Serena is teaching in Via Terracini, okay? And we have also some news for you about internship and thesis. If you are not hurried, we can discuss next week or in 2 weeks from now. But just to give you an anticipation, for the internship is really a big problem to find it outside the university at this time, but we can propose something internal to the university if you like, and we can also propose a subject for the thesis. But we can discuss with more details later, okay?
Okay, Professor, thank you.
Yeah, no problem.